Hey there, and welcome. Today, we're diving into a topic that can be a real head-scratcher for chemistry students: resonance. On the surface, it seems simple enough, but underneath, there's this incredible story about how science actually works. So let's get right into it. It all really comes down to this one question. You've got these two major theories that describe chemical bonds, right? But they see the world in completely different ways. So where on earth does the idea of resonance actually come from? Which camp does it belong to? And there it is. If you just want the quick, multiple choice, test day answer, resonance is 100% a creation of valence bond theory. Full stop. Case closed. Or is it? Yeah, not so fast, because the real story here is honestly so much cooler. It shows us the scientific models aren't these perfect, absolute truths. They're just tools. Really powerful tools, mind you, but each has its own limits and blind spots as we try to get a handle on reality. Okay, so let's start with valence bond theory. We need to figure out why it was even necessary to come up with this concept of resonance to begin with. At its core, valence bond theory is super intuitive. It's the chemistry you probably learned first, your classic Lewis structures. You imagine two atoms and boom, they share a pair of electrons and a nice, neat little line between them. We call this a localized bond. It's clean, it's simple, and it's incredibly useful for a ton of stuff. But it's not the whole story. And the poster child for its limits is the benzene molecule. So using this dot and line model, you can draw a perfectly valid structure for benzene with alternating double and single bonds. Looks good, right? But wait a second, you could just as easily have drawn this structure with all the bonds flipped. The problem is, when we actually measure a real benzene molecule, all the bonds are the exact same length, somewhere in between a single and a double bond. So which drawing is right? The answer is neither of them. Our simple model just fell apart. This is where the brilliant Linus Pauling enters the picture. He came up with the idea of resonance, but, and this is so important, not as a physical process, but as a mathematical patch. The key takeaway is this: the molecule isn't doing anything. It's not shifting or changing. We, the scientists, invented the concept of resonance to fix a problem with our drawing. And this leads us to the single biggest misconception about resonance, hands down. It is not a molecule flipping back and forth between two different forms. It's not oscillating. It is one single unchanging thing, a blended average that we call a resonance hybrid. I love this analogy because it makes it so clear. Think of a griffin. A griffin is a hybrid, part lion, part eagle. But a griffin doesn't wake up on Monday and decide to be a lion, and then on Tuesday it's an eagle. No, it is always a griffin. In the exact same way, benzene is always just benzene. It's a single, stable hybrid that we just happen to need two different drawings to fully describe. Okay, so valence bond theory has to invent this clever idea of resonance to fix its model. But what if there was another way to see molecules, from the ground up? Let's check out how a totally different theory handles the exact same molecule. And this brings us to molecular orbital theory, or MOT. This is a complete paradigm shift. It basically says, forget the idea of neat little bonds between just two atoms. Instead, MOT says electrons belong to the whole molecule all at once. They exist in these huge molecular orbitals, which are like giant electron clouds that can spread out over every single atom. The electrons are totally delocalized. Now here is the beautiful part. From the perspective of molecular orbital theory, there is no benzene problem. There's nothing to solve. It doesn't need a patch, it doesn't need a special concept. It just looks at benzene and says, well, of course the electrons are smeared out over the whole ring. That's their lowest energy, most stable state. You see, the problem was never with the molecule itself, it was a limitation of our first model. So now we've got two completely different ways of thinking. We have VBT with its necessary invention, resonance, and we have MOT with its elegant, delocalized orbitals. Both are trying to describe the exact same physical reality. So how do they really compare? Let's just lay it all out. VBT is kind of a bottom-up approach, right? It builds molecules by sticking atoms together, which forces it to use the idea of resonance for tricky cases like benzene. MOT is top-down. It looks at the whole molecule at once, which naturally leads to the idea of delocalized electrons. Two very different paths trying to get to the same destination. Now, at this point, you're probably thinking, okay, if molecular orbital theory is more accurate and kind of more elegant, why on earth do we even bother with resonance anymore? And that is a fantastic question. The answer really comes down to one word: practicality. Resonance, for all its theoretical weirdness, is just so incredibly useful. It works perfectly with the simple dot and line drawings we use every single day. It's visual, it's easy to grasp, and most importantly, it gives chemists a massive amount of power to predict how molecules are going to behave and react. It's become the fundamental language of organic chemistry. And I'm not exaggerating when I say it's the language. It's so deeply embedded in how chemists think and communicate. Get this, something like 90% of introductory organic chemistry textbooks use resonance as the main way to explain this stuff. It's an indispensable tool, even if we know it's not the most complete picture of reality. And this brings us back to where we started. At the end of the day, both of these are just models. They're useful stories we tell ourselves to make sense of the universe. Valence bond theory gives us an intuitive tool that's a little flawed. Molecular orbital theory gives us a more accurate one that's a lot more complex. And that leaves us with a really deep question. When our best scientific models are just different descriptions, which truth do we choose? The one that's the most useful or the one that's the most accurate?